Hello, welcome to this video about motion under gravity. It's a continuation of the video series on motion and kinematics, and in this video we're going to talk about how gravity affects motion, or basically what happens to motion under gravity. Now, the one thing that we need to understand is that we are talking about gravity after having studied constant acceleration, so it really doesn't take much to make the connection that gravity indeed would be introduced to as a constant acceleration, or a form of acceleration that does not change. So if we know how to deal with constant accelerated motion, then we would know how to deal with gravity in the same manner. It is just a category of acceleration which is very more common and is quite natural in that sense, and hence it makes more sense to talk about it right after studying acceleration or constant acceleration. So here it is, and to begin with that, let me get rid of this rather elaborate image, and like that. Alright, so motion under gravity. Now, we all know that the Earth is a round sphere, something like that, slightly bulged at the poles, but that's of no consequence at this point. And imagine, if you will, we have a body right there. What happens to this body is that if we let it loose, if we let it fall, then it's acted on a force applied on it by the Earth, and that is the force of gravity. Now that can be dealt with if we know Newton's laws of motion, or the second law of motion by Newton, and even if we don't have the knowledge of that, well, it would suffice to know the fact that any body which is left in mid-air will experience a gravitational force in the downward direction, and that is given by g. Now, g is experimentally measured to be around 9.81 meters per second square inverse. Oh, yeah, so that is how you would talk about accelerated motion. So that is to say that, remember, that apple that fell on Newton's head, well, that apple was falling on his head, somewhere there, with an acceleration of 9.81 meter per second square inverse. And that is how it gains speed. Now the thing is, this gravity, or g, or the motion, or the accelerated motion, does not change in the sense that gravity, the acceleration due to gravity, remains constant throughout its motion. So say we let a ball loose there, then that ball will come down to the center of the Earth with the gravity of 9.81, but even at all points of time throughout its motion, it will experience the same gravity or the same acceleration at all points, no matter what its velocity would be. The only difference comes when the ball finally impacts ground, and the only time this stops acting is when the ball reaches the ground, and that is when you have many other forces at play, and therefore talking about gravity in that state is pretty much useless. So if we know what happens to a car that is accelerated through its engine at some constant acceleration of a, and we know how to study these kind of motion, we can evaluate the final velocity, knowing the initial velocity, the time throughout the motion, and also the displacement of the car, then we should be well equipped to study motion of a naturally accelerated body under the force of gravity. So that is basically it. Now, there is one example that will really help to understand what happens to a body under accelerated gravity, and we would do that right now. So let me get rid of this for the moment, and let us deal with, in this video, let us deal with just variables. So say you have a ball of mass, well, it doesn't really matter, you have a ball at height capital H from the ground, and you let it go at that instant, and you calculate its velocity as it falls down. So at some point of time, at t equal to 0, the ball was in mid-air. At t equal to some other time, say t half, the ball might have been at, say, h by 2 height, and finally at time, well, t equal to capital T, the ball was at the ground. But it had not yet impacted ground but was very close to the ground. So at that point, its height from the ground was very, very small, very much equal to 0, but it hadn't yet hit the ground. So those are the three instances, and let us try to evaluate what happens to the ball at different times. So we all know so far, as what we've discussed, that the ball would be acted upon the acceleration in the downward direction. So with that in mind, we call that acceleration g, and for now, let us keep in mind that g equals 9.81 meter per second square, and that's about it. Let's talk about g in the form of variable at this point. We can obviously substitute 9.81 and get the exact values, but let us just consider it in terms of g. So what do we know about a ball that has been left in mid-air? Well, if the ball has been left in mid-air, then its initial velocity must be 0. It's as though the ball was at rest and we let gravity act on that. So initial velocity is 0, as I've stated here. The final velocity could be evaluated at two instances. One here, we call it v 1 by 2, or v half, and finally we call this velocity capital, or just small v. So these are our two velocities, and let us try to evaluate what happens to both of them at different times. So the first velocity, which is v1 by 2, well, this is the velocity when the ball has reached a height of h by 2. It started by initial velocity of 0 and the final velocity of v1 by 2. So what do we know about this velocity? Well, we have many equations to deal with problems like this. Let me write those equations down to further help us. So final velocity equals initial velocity plus acceleration times time. The total displacement equals ut plus half at square. And final velocity square equals initial velocity square plus 2as. So those are the three equations. Let us try to use those three, or any one that works, to evaluate v1 by 2. So in order to do that, we must realize that, okay, so if we employ the first equation, we get v1 by 2, or this velocity here would have been the initial velocity, which was 0, plus acceleration, which was g, and the time that it had taken for the height of h by 2, and that would have been t1 by 2. Now the thing is, do we really know what t1 by 2 is? The answer is no. What do we actually know? We know h. We know the height from which we drop the ball. So we must convert t1 by 2, or t half, into the height h, and then use this equation. That is when we would know what the velocity would be in terms of gravity and the height that we know. So these are the only two quantities that we know, and let us try to get v half in those terms as well. So, well, the first equation did not work. The second equation is s equals ut plus half at square. Well, if you see in the second equation as well, we have the time intervals, t and t square. So that would also not work, because they would also use up t1 by 2. So the second equation is also of no help at this point. We want to get answers only in terms of g and h. Well, if you really want to get those values, then we must use the last equation. The last equation says the final velocity square equals initial velocity square plus 2as. Alright, so final velocity square is v half square, initial velocity square is just 0 square, plus 2, and a, which is g, and s. S is the height it has fallen. So if this was the initial position of the ball, and this is the final position of the ball, then this would be s1 by 2 vector. This is the displacement vector for the first, for t half duration of motion, and so that would be pointing downwards. Since gravity also points downward, both these will multiply to give a positive value, and hence we would just write this to be h by 2. So there we have it, v half square equals 2 times g times h by 2. The two get cancelled out, and you're left with v half equals root gh. So if the ball is in the center, is at height h by 2, from its initial height of h, then it would have gained a velocity of gh root meter per second. So that is how much the velocity would have been. Alright, so that makes sense. But can we evaluate what the time would be? How much time would have elapsed for this ball to develop or gain a velocity of root gh? Well, we could do that now using the first equation. So we now know that v half equals root gh, and that must be equal to 0 plus g plus t half. I've basically used the first equation again. So final velocity equals initial velocity plus g times t. And solving that gives us t half equals root gh divided by g, and that's the same as root by h by g. So this is the time over which the ball falls the height of h by 2. So there you have it. You know the times for half of the motion. So let me write this down here somewhere. V half equals root gh. T half equals root of h by g. So now we know both these variables and we're good to go. We do the same thing for the entire motion. The entire motion can be dealt with the final velocity to be v, initial velocity to be 0, time to be the capital T time, g to be acceleration, and s here would be h measured in the negative direction. So there you have it. Those are your variables. Alright, so the first equation for the total motion of the ball until which it falls to the ground would be final velocity equals initial velocity, which was 0, plus g times t. Well, t here would be capital T, and g would be basically g. We therefore have v equals gt, like before. But do we really know what capital T is? Well, no. But we can definitely get that in terms of h eventually. So let's try to do that again. Using the third equation. So the third equation yields v square equals u square, which is 0 square, plus 2. Now the acceleration is g in the negative direction, and s is the displacement vector. Now the displacement vector here would be all the way down there, the white arrow. And this would be the s vector, and this is the total vector all the way to the ground. This is an s, and its magnitude would be h, because that is the height of the ball. So therefore, s would be replaced by capital H. You can use this equation, you can take roots on both the sides to give you v equals root of 2 gh. So this is your final velocity. If this is the final velocity, can we calculate the time? Well, we can substitute this back into this equation to get root 2gh equals g times capital T, or the total time over which the ball falls to the ground is 2h by g. So this is your total time again. Now you see there are certain things which are very, very interesting. The interesting parts are that initially at half of the motion, the velocity of the ball was root gh, and the time over which it fell this h by 2 distance was h by g root of that. Eventually, when the ball was at the ground, the final velocity was 2gh under root, or root 2 times its half velocity before. And the total time that it took to fall that much height was 2h by g, or again, root 2 times the t half value. So there it is. That is how you would get all your variables. Now, it may seem unfair for now that we haven't used the second equation. Well, we can use either of the two equations to study any motion, but many times it is just helpful to use all the equations to see that our understanding is right. So I'm going to do that now. At this point, our problem has been solved. We know how long the ball would take to fall to the ground if we put it at the height of h, and if we know the gravitational acceleration, that is g. We also know the velocity at which the ball would impact the ground, and that is 2gh root of that. And basically, we know every dynamical variable that there is for a falling ball from rest. But now what we're going to do is we're going to take the second equation, the last remaining equation that we haven't used, and try to fit in these parameters. So let me get rid of this for the moment, remembering that our final time over which the ball fell was 2h by g root of that, and the final velocity was root of 2gh. So let's try to see if we get s equal to h. So if s equal to h, then our understanding would have been complete and would have been correct. So let's try to see if that is the case. Is s equal to h? In order to do that, we say S equals the total displacement vector from the initial to the final position equals ut plus half at squared. Now, we know that u was 0 because initially the ball was at rest. And finally, you have to put in the other term as well, so that's half of a t squared. Now, a here would be g, and t squared would be capital T squared. So therefore, S would be half of g times capital T squared, or 2h by g square of that. Now, square of root is basically the number inside. You get g by 2 times 2h by g. Cancel the g's, cancel the 2, and you're left with S equals h. So that's good. Now we know that indeed S was h, or the displacement vector was h in its magnitude. So that is how you would also check. You can also check whether or not your analysis of the problem is correct by ensuring that all the three equations are satisfied. But remember, if only two of them are satisfied, any two of them, the third one should be satisfied if you have proceeded in the correct manner, but you could always check it like I did. So there you have it. That is how you would ensure that your problem is right. And that is how you can also understand what happens to a ball that you leave in mid-air with 0 velocity and you let it fall down. So I hope this video made sense. I hope it helped you understand the impact of gravity and how we would deal with similar equations of motion that we have studied so far, just knowing that gravity acts in terms of constant acceleration, and its value is given by 9.81 meters per second square. So I hope this video made sense, and I hope it helped you, and all the very best.